Hi, my name is Marlyse Reeves, and I'm a PhD student in CSAIL at MIT. I work with Brian Williams in the Model-Based Embedded and Robotic Systems group. My research has been focused on designing decision-making algorithms for multi-agent autonomous systems operating in dynamic and hazardous environments. In the past few years, I have applied this research to the field of ocean exploration. Last November, in collaboration with the Woods Hole Oceanographic Institute and the University of Michigan, we participated in a deployment to the Colombo volcano, an underwater caldera off the coast of Santorini, Greece. Our objective was to use a small fleet of autonomous underwater vehicles, or AUVs, to explore the caldera in search of evidence of life in extreme environments. The deployment was an analog demonstration of a potential future mission to the under-ice oceans of the moon Europa. The AUVs that we were working with can operate for hours at a time on a single charge, and the ocean currents make the environment unpredictable. To compensate for this, I developed a planner capable of generating coordinated trajectories for multiple agents to achieve many activities over a long time horizon, adapting trajectories as necessary on the fly. This is achieved through a combination of model predictive control and continuous time convex trajectory optimization. Looking forward, I am interested in expanding the capabilities of our autonomous system architecture to allow agents to actively learn while they're executing in the world. In our previous deployments, we assumed that we had accurate models of the AUV behavior. In reality, these models turn out to be insufficient or too imprecise when unforeseen situations and failures occur. In the face of model uncertainty, humans are able to quickly experiment and learn new models to continue on. For example, imagine twisting your ankle while running an errand. Your old model of walking is no longer applicable in this situation. You experiment with your footing to gather information about how much weight you can place on your injured leg. Using this information, you learn a new model of movement, and you limp to carry on with your errand. I'd like to imbue autonomous systems with the same notion of cautious, directed experimentation in the face of model uncertainty. Leveraging research in information-based planning and reinforcement learning, an agent can plan information gathering actions to improve its own behavior model without taking unnecessary actions or risks. Once a new model is learned, execution of the original task can proceed. My hope is that this work will allow systems to be more robust in the face of uncertainty and equipped to handle non-terminal failures and changes in the environment with limited to no intervention by a human. These characteristics become increasingly important as we task robots to explore more places beyond the reach of even human communication, such as disaster areas, ocean depths, and the outer solar system and beyond.